Hello and thanks for tuning in today. In this video, we will take a look at a CQRS implementation in Spin. The app, which we will explore in a second, has components written in Rust and a component written in Go. On top of that, we used local service chaining capabilities provided by Spin to do inter-component communication in a fast, reliable and secure way. So without further ado, let's get started. Looking at the architectural diagram of our app, we can see that our app consists of two orange components written in Rust and a blue component, meaning that this one is implemented in Go. On top of that, we have some sort of data storage, right? Because we want to persist data. So we decided to go with SQLite, because using SQLite from within a Spin app is super simple. However, you can also use different systems like, for example, PostgreSQL or MySQL to persist your data from within a Spin app. If we take a look at the gateway is responsible for laying out the public HTTP API of our Spin app. So this is where we register get endpoints, post, put, delete endpoints. All those sorts happen in the gateway. In CQRS, requests that want to read data are referred to as queries. So all read requests go through the gateway into the queries component. The queries component and the commands component are often referred to as backend components. And this is because they are not exposed to the outer world, right? There's no endpoint that you can invoke from outside of the Spin app to immediately invoke a query. You have to go through the gateway. The gateway is the only component that is allowed to call into both queries and the commands component using local service chaining. We will look at local service chaining in detail in a couple of minutes, but it's important to understand at the architectural level already. So in the case of a query, the Go code is responsible to construct T-SQL commands that are optimized for reading data. On the flip side, the commands component is responsible for creating T-SQL commands that are able to validate data, to store data using the third normal form in our data storage, right? So those are different disciplines, and that's why it's a common pattern in CQRS to separate both. And in our case, we took it one step further. We used different programming languages for implementing queries and commands. All right. So that being said, let's jump right into VS Code and let's have a look at the Spin app. The Spin app itself has been created using the HTTP empty template. Using the HTTP empty template allows you to add multiple components into a single Spin app and maintain a clean structure within the source code representation. Within the application manifest, we are able to spot all the components that we saw in the architectural diagram a couple of seconds ago. And let's start by looking at the gateway component. The gateway component has been created using the HTTP Rust template. That's why we have an HTTP trigger configuration. For this one, for the gateway, we use the wildcard pattern to tell Spin that it should invoke the gateway component for every incoming request. More interesting is the gateway component configuration, especially the allowed outbound hosts property, which we set to https://anything.spin.internal. And spin.internal is the important essence of that value. If guest code from within the gateway component tries to create an outbound request with an origin ending with that suffix, the spin host runtime knows that the intention is to do local service chaining. So instead of building and sending an HTTP request, the spin host runtime instantiates the desired component and invokes it directly. So there's no network between the gateway and the invocation and the query component, for example. However, this configuration is a little bit loose, so to say, right? So we allow the gateway component to call into any sibling component. Instead, we could be a little bit more strict and say, hey, the gateway component is only able to call into the queries component and the commands component. So this would be a little bit stricter. However, I find using the wildcard pattern like this super useful if you're not 100% sure if those are all the components you will build as part of that spin app, right? So by using this syntax, you could add another sibling component and the gateway would be immediately able to call into that component. All right, let's move on to the component configuration for the queries component. Remember, the queries component is a backend component. It has also been created using an HTTP template. To be more precise, this one has been created using the HTTP GO template. However, instead of providing a route pattern, we set the route as private. By setting the route as private, we ensure that it is not possible to call into the queries component from outside. Instead, the queries component is only addressable from components in that spin app using https://queries, that's the name of the component, .spin.internal. On top of that, the queries component has access to a SQLite database called default. If we look at the component configuration for the commands component, we can see that it also has been created using an HTTP template. Again, this was HTTP Rust. We set the route to private to get rid of a public endpoint for that particular component, and we allow our commands component access to the default SQLite database as we did for the queries component. Speaking of databases, there is a migrations.sql file in this spin app, which is responsible for provisioning the database scheme and maybe seeding some sample data. So you can use SQL files in different environments. So for example, speaking about my local developer experience, right, I use spin up to start a spin app. However, I can append --SQLite and point to a SQL file to ensure that spin, upon bootstrapping the app, executes this SQL commands against the default SQLite database. Also, if you think about deploying your spin app to Fermion Cloud, to SpinCube, or to Fermion Platform for Kubernetes, you can use migrations files to provision the database scheme and get your seed data into the database. So the database scheme for this sample application is super simple, right? It consists of just two tables. We have the employees table and we have the addresses table. Between those tables, we use a one-to-one relationship, meaning one employee can have exactly one address in our application. On top of that, we set onDelete cascade, resulting in if someone deletes an entry from the employees table, the related or corresponding address will also be deleted from the addresses table without you having to do anything, right? The database system takes care of deleting the reference or the referenced entry in the addresses table. We seed some sample data, so we have John Doe as an employee in our database, and his address is set to 1234 Main Street in Boston. Now that we have a common understanding of the overall spin app, it's time to dive into the components. And again, let's start at the top with the gateway. So the gateway is using the router provided by the Spin SDK for Rust to register the HTTP endpoints, so the public API of our Spin app, right? We have get endpoints for our queries to retrieve a list of employees and to retrieve an employee using its identifier. We have additional endpoints using corresponding HTTP methods based on the scenario. So to create a new employee, we register a post endpoint. To update an employee using its identifier, we register a put endpoint. And for deleting an employee using his or her ID, we register a delete endpoint. First, let's start with looking at the queries implementation. So within this implementation, I tried to reduce code duplication. This is why both get employees and get employee by ID almost immediately, in the case of get by ID, call into the execute query function. So both functions have to construct the URL pointing to the desired query. In the case of reading all employees, it is queries.spin.internal/employees. In the case of reading a particular employee, we extract the ID from the route and concat that one to the same URL. So we end up with queries.spin.internal/employees/SomeGUID. In both cases, we hand over the URL to the execute query function. So let's have a look at that one. This one uses the request builder to construct a get request pointing to the Spin internal URL of our queries component. We use the send function provided by the Spin SDK to send the outbound request. Remember, the origin ends with .spin.internal, so there is no HTTP going out somewhere, right? The Spin host runtime recognizes that suffix and decides, oh, that is a local service chaining call, so I don't have to do HTTP. I can simply instantiate the desired component and send a request there. Obviously, this sending mechanism is async. That's why we wait for the result, and we use the question mark operator over there. So in the case something goes wrong, right, we terminate execution early by simply returning an error. The underlying Spin runtime catches that error and returns back an HTTP 500. So we don't have to match everywhere and check for the error. If we want to treat it as a simple HTTP 500, as a simple internal server error, we can use in Rust the question mark operator and have the Spin runtime return an HTTP 500. So if everything works, I mean the backend could still send us an HTTP 500. That's, from our point of view, it's not a failure. It's just some sort of response that we receive in this variable, which we pass over to parse result. And this is super nice about, local service chaining and, for example, CQRS, right? So we use the parse result method for both queries and commands. So every HTTP invocation does something, calls into some backend component, and every response we get back from some backend is sent to the parse result function, which can do, interesting and useful things. So for example, if the backend service returns an HTTP 500, and we will look at those HTTP 500s in a second, right? We lock the response body to standard out so that we have some information of what went wrong. If you're building APIs, it's a good or best practice to not send implementation details or information that could leak implementation details across a boundary such as HTTP. So we take that potential sensitive information, log that to standard out, and return a simple HTTP 500 with the body internal server error to the callee. So we don't leak any implementation details anymore. We'll come back to the gateway and have a look at commands in a few, but let's have a look at the queries component. So this one is using Go. And the interesting thing is, in local service chaining, although this is a backend component with no visible endpoint, we code that component the same way we coded the gateway, right? So again, we use the router, this time from the Spin SDK for Go, to define our API and lay out the endpoints. In this case, let's again go into get employee by ID over here. We read the identifier from the route parameter. If it is length of null, we return bad request. If it is valid, we call persistence get employee by ID. That one uses SQLite APIs provided by the Spin SDK to read a single or particular employee from the database, including its address. So, as you may already guess, the SQL command is selecting all the columns from both tables, employees and address, using an inner join to express the relationship between those two tables, and setting the filter to filter only for the employee with that particular ID that we received over HTTP. So pretty straightforward. Over here, we then iterate over, or in the case of an error, we return nil as our employee details model, and we return the actual error that we receive from that query call. So there could be useful information in that error message, right? Information that we don't want to send to the callee, but that would be pretty useful in the case of troubleshooting or trying to reproduce an error. So if everything went well, then we construct a new instance of employee details model. We fill in all the properties and we return back that employee model. Let's go back to this section over there where we call get employee by ID, right? If there is an error, we construct a meaningful error message, say, hey, there was an error while loading a specific employee from the database. And by the way, this is the error, right? So we use sprintf over here to use string interpolation and bring in the actual error message. So this is something you could do with the backend service where the gateway sitting in front of it takes that information, prints it to standard out, but then sends a clean internal server error message to the callee. Now that we have dealt with the error, we still have to investigate what this found variable is, right? It could be nil. It could be nil if we provide a GUID that does not exist in a database, right? In that case, we will return a 404, a simple not found. However, if found is not equal nil, we create a new encoder from the JSON package and send back the employee details model to the gateway. Let's get back to the gateway one last time and let's have a look at a command. And I think we should look at the update employee by ID command, right? So this one, we again extract the ID from the route parameter and we construct a URL as we did already for our query, but this time, you may already guess, we are pointing to commands.spin.internal. Speaking about commands, there are several commands that have a payload. So for example, creating or updating an employee, you usually send the data as the payload of that request. However, there are other requests or commands, like for example, deleting an employee using its identifier, where you don't have any payload. In order to deal with both scenarios in a unified way, we extract in the context of creating and updating an employee, we extract the content type HTTP header from the incoming HTTP request and send that along with the request body to the execute command function. In the case of deleting an employee, we also extract the ID, we also construct a URL. However, we don't expect this scenario to have any sort of payload. We simply send none for the content type and none for the payload. So the execute command method can look at both, or in this case at the content type, and say, hey, if I received some sort of content type, let me create a new HTTP request, pass the received content type down to the backend service, because that one needs to know how to deal with the data. If we did not receive any content type, then we create a simple post request with the URL that we constructed before and provide nothing as request payload. In both scenarios, we set the accept header to instruct the backend service. Hey, I am interested, or I'm the gateway, I'm interested in JSON. Again, we use the send method to send the request to our sibling component. And again, we call into the parse results method to parse the response that we receive from the backend. In this case, all calls go to the commands component. So let's explore that one before we give it a try. This one's again written in Rust, so you are already familiar with the router, right? There are different ways to approach that. I decided that my commands should all be post endpoints to unify how someone, like the developer who is in charge of the gateway, could interact with the commands component. Let's stick with the update employee scenario for now. Let's have a look at the implementation. The commands component may have some sort of business logic. Business logic could be something like validating incoming data, like, generating new UUIDs, stuff like that. And that's why this one has additional dependencies. So we're using the 30 and 30 JSON crate to deal with incoming data, right? And we use the UUID crate with the v4 feature, to roll new GUIDs or to verify GUIDs that we receive from the callee. We take a look at the request body and we try to deserialize it from a raw vector of bytes into an instance of the update employee struct. So I'm a big fan of having dedicated API models per scenario. Although in a simple CRUD scenario, create models and update models are often the same, I don't use the same model. I always stick with dedicated models because it makes refactoring easier and does not have some shared meaning. If we are able to deserialize whatever we received as payload into an update employee model, then we will continue. Otherwise, we will just return back an HTTP 500, which could be refactored into an HTTP 400. Next, we extract the identifier from the route parameter and we call into persistence module over there, and we also have an update employee by ID method. So let's go into that one, and you may already guess what happens. Updating an employee, because we receive both employee and its address, it should only be treated successful if both tables were updated successfully. We construct a command to update the employee table and one to update the address table. We end the transaction, and if all commands were executed without resulting in an error, we return back an employee updated model, providing the latest and greatest data from that particular employee. Let's go back to our implementation. We use pattern matching to get back the updated, which, as you can see, this is an option of employee updated model, meaning there are situations where we get back something like an updated employee, right? But there could be situations where we get back nothing or none. If the user provides an identifier that we are not aware of, that's not in our database, that one could be none. So we check, hey, if there is some, then we go ahead and serialize that updated entity into a vector of bytes and create an HTTP 200 response and send it back to our gateway. If there's none, we return back an HTTP 404 identifying, hey, everything was great, however, we don't know the ID you provided. That being said, it's time to give it a shot. So let's move over to terminal in VS Code. Do a spin up -- SQLite at migrations.sql -- build. So this one is not just starting the spin up, it's building all the components. It's executing the migrations.sql upon bootstrapping, and then it's bootstrapping the spin up. And we end up with being presented with the path where we can find our database, and we have our app running on localhost port 3000. Let's move over to Postman and let's call into the employee's endpoint. As you can see, we get back an array with Doe, John. Next endpoint will be a command, right? So we want to add a new employee to our database. He's called Mike Smith and he lives in New York. So let's give it a try, invoke that one, and we get back a 201 created with the identifier being OA something ending with D1. Let's go ahead and update Mike Smith and rename him to Jerome Smith, and also update, I think the number is updated. Yeah, it is from 123 to 321 in the Second Avenue. So let's invoke that one, and we get back Jerome Smith living in 321 Second Avenue. You can also invoke the query to get those employee details. And as you can see, right now we get back the representation using a dedicated first name and last name field and all the properties from the address. So before deleting Jerome Smith again from database, let's go back to get all invoke that one once more and seeing both entries being returned over there. And finally, let's delete Jerome Smith, we get back a 204 with no content, go back to get all, and we're back to just having John Doe in our employees table. With that, we made our way through a CQRS implementation in Spin using multiple programming languages. So we had Rust on the one side, we had Go on the other side. We were using local service chaining, which is super great if you want to do inter-component communication and you don't have to go, all the way using egress and ingress again. So you could call directly to your backend components. With that said, I hope you liked it. Leave a comment down below where you think local service chaining would be super useful when building Spin apps. And with that, see you next time.